Hello, everyone. I'm Samuel Buckner,
And I'm Chris Hayner.
and today we are proud to present our research on hazard-aware landing optimization for autonomous systems conducted at the University of Washington Department of Aeronautics and Astronautics. We will start with a brief introduction. The objective of our research is to develop a framework that enables autonomous aerial vehicles to land safely in unknown environments with only depth information on their surroundings, such as LiDAR. We conduct this by closing the loop on perception and action, or path planning. To this end, two key algorithms have been developed and integrated closed loop in the AirSim simulation environment: hazard-aware landing site selection, or HALS, and adaptive deferred decision trajectory optimization, or adaptive DDTO. In terms of problem motivation, we consider multiple exciting potential applications, such as technology relating to the Mars helicopter, as well as large-scale package delivery operations.
Now we are going to introduce the hazard-aware landing site selection algorithm. The course hazard detection focuses on identifying larger hazards and safe regions within the scope of the entire observed map. Initially, a point cloud is captured from a simulated LiDAR sensor, and a function is found from a coarse linear interpolation from which the surface normal is created. A surface normal encapsulates terrain gradient information, where the RGB values correspond to the unit normal vector for that location in the environment. 30 Monte Carlo samples of the surface normal are propagated through a Bayesian segmentation network using Monte Carlo dropout. The variance is thresholded such that only the 10% most certain classifications are considered safe and is combined with the mean using a logical AND operation, creating an uncertainty-aware safety map. The medial axis transform provides a quick and efficient method to skeletonize the uncertainty-aware safety map. The skeleton is searched and a region is placed on the largest value on the skeleton. This region is then masked, and the process is repeated for n max times. This ensures that the center of one region cannot lie within another. The fine hazard detection focuses on determining landing sites within the scope of each region as identified from the coarse hazard detection step. The location and radius of the identified regions are transformed from the image frame to the world frame, and a subset of the global point cloud that lies within that region is found. For each local point cloud, a surface normal is found by performing a fine linear interpolation which allows for the detection of smaller hazards that were previously missed in the coarse hazard detection step. The surface inclination is found from the surface normal, which is thresholded such that the inclination above a value alpha is considered to be unsafe, resulting in localized safety maps. The medial axis transform is again applied to each local safety map, and the largest inscribed circle is chosen as the landing site for that region, ultimately resulting in NMAX landing sites, which are passed to adaptive DDTO.
Next, we will look at the adaptive deferred decision trajectory optimization algorithm. At a high level, we want to consider multiple targets simultaneously and generally move in their direction. Eventually, while descending, we may select a target to lock onto once we have enough information about it. We can start by considering a single target trajectory optimization problem between initial condition x0 and terminal condition xf, with a target safety bounding radius r. The vehicle is subjected to gravity and affine dynamics with a minimum cumulative thrust objective. There are constraints applied to the thrust pointing direction, thrust magnitude, and velocity magnitude, both vertically and laterally. We can then use a technique known as deferred decision trajectory optimization, or DDTO, to augment this problem to consider multiple targets. A naive approach would be to solve to each target individually. However, DDTO instead adds an additional constraint to maximize the time duration to keep all targets in consideration simultaneously, using quasi-convex optimization. We constrain each new solution to be epsilon suboptimal to the previously shown individual solutions. This process can be repeated iteratively, pruning one target at a time, to produce a tree-like structure of trajectories that maintain deferrability. There is a problem, however. Targets can be lost while executing the solution due to perception updates, dynamic changes in the environment, and just due to the fundamental nature of DDTO's tree-like structure. The solution is to adaptively recompute DDTO solutions whenever the target count falls below a minimum threshold. Here, we consider a landing simulation with 7 targets. As the simulation plays out, we can see that targets are lost for various different reasons. Ultimately, the minimum target threshold is triggered and a new DDTO solution is computed. This process repeats iteratively until a guidance slot condition is achieved, such as an altitude trigger, at which point the lander commits to its chosen destination. More information on the algorithm structure is available in the paper.
Finally, we are going to present our simulation results. Microsoft AirSim was used to simulate cloud rotor dynamics. The maps were made using the NASA HiRISE digital elevation models. Successful landings were performed in a variety of environments, showing the domain robustness of our architecture, ranging from flat, mountainous, dunes, and plateaus. Open source demonstrations of both algorithms are available on our GitHub. Finally, we, the authors, would like to thank all of those who have supported this work. Thank you for watching.